In today's lab experiment, we're going to investigate the relationship between the pressure and the volume of a gas in a container. We'll vary the volume and we'll observe the pressure. So the volume is the independent variable plotted on the horizontal axis, and the pressure is the dependent variable, and that'll go on the vertical axis. When we heat up or cool down a gas, like in a balloon, it's easy to see that there are changes to the gas. So that might affect the pressure. So we'll need to control that variable. Fortunately, it's pretty easy to control temperature because we'll be working in an environment that's heated and the room temperature won't change very much. If you've ever pumped up a tire, you know that changing the number of particles in the tire also has an effect on the pressure. So we'll have to control for this variable by making sure that the number of particles doesn't change when we measure the pressure, no matter what the volume is. This is also pretty easy if we just make sure that the container stays sealed. We're going to be using a pressure sensor that can be read by a computer with the help of a special lab interface. The container that we're going to use will be a plastic syringe, like the kind medical people use to inject drugs into people's arms. Ours won't have a needle on it though. It will just attach directly to the pressure sensor. The gas we'll be using is the easiest gas to find, air. We'll set up the data collecting unit so that it measures the pressure when we tell it to, and it also asks us to enter the volume of the syringe. Easy peasy. So first, we'll add a medium-sized amount of air to the syringe, about a half a syringe full. The exact amount is not too important. Then we'll attach the syringe to the pressure sensor. Then, after the particles are sealed in by the connection, we'll make sure to never unseal it until we're done taking all of our readings. Now we just adjust the volume to several different values, and each time we'll stop, measure the pressure, and tell the app what the volume is when it asks us to. When I did this experiment with 10 milliliters of air at room pressure, and then compressed it to 2.5 milliliters, 5.0 milliliters, 7.5 milliliters, and then expanded it to 12.5, 15.5, 17.5, and 20 milliliters, I got this result. Just visually looking at this result, it does not look like a line is going to be a good model for this relationship. In fact, when I apply a linear fit, it tells the story even more clearly. The correlation value is not great. 0.9405 does not indicate a very good line fit. And visually, you can see that the line does not follow the pattern that the points are following. The shape of this curve suggests that a good way to transform this data and linearize it might be to plot the inverse of the volume values. That's because this could be a hyperbola relationship, and that's a pressure, in this case, inverse of volume, should give a straight line, if that's true. So I tried it, and in fact, it worked out. When I replotted pressure against the inverse of volume, I find that I get a correlation value that's much better, and that confirms that this line would be a good model for the relationship. But the equation for this line is pressure is slope times, not volume, but 1 over volume, or inverse volume. The vertical intercept, 39.69 torr, is much, much smaller than the highest pressure value, and so it's okay to throw that out of our relationship. So what's our conclusion? Because 1 over volume plotted on the horizontal axis made a straight line relationship with pressure on the vertical axis, the equation for that line is pressure is K times 1 over V. So pressure varies inversely with volume, is what we say. If we multiply both sides by V, we get a result that I think is more useful in interpreting this relationship. Pressure times volume is a number that never changes. That product can't change. So here's what that means. Whatever happens to the volume, the reciprocal or the inverse has to happen to the pressure, and vice versa. So if we cut our volume in half by squishing the gas into a smaller container, that means the pressure is forced to double. On the other hand, if we were to expand our volume to double its original value, that would force the pressure to drop to half of what it used to be. That's what an inverse proportionality does. So whatever happens to either of these two values, the exact reciprocal or inverse would have to happen to the other one. That's a relationship between pressure and volume. as long as the temperature is controlled and the number of particles doesn't change.